Alright guys, so I promised you I'd put together a crash course video for electrochemistry, so here we go. So, where I want to start is oxidation states. There will be some questions dealing with oxidation states on your exam and future exams as well. So, the main rules are that oxygen is always -2. The only time when it's not -2 is if it's in hydrogen peroxide, which is what you see here, in which each oxygen is -1, or if oxygen's by itself. If it's a free element, if it's by itself. In that case, the oxidation state of oxygen is 0. Another rule to know is hydrogen is always +1 unless it's behind a metal. If it's on the back end of a metal, then it is -1, or if hydrogen is just by itself, its oxidation state is 0. Another thing to know is that ions have oxidation states that are equal to their charge. So if I had Fe3+, then my oxidation state would be 3+. And then last but not least, the sum of the oxidation states must equal the overall charge of the compound. If you see an outlying charge of the compound, all of those oxidation states must equal that charge. If you do not see a charge outside of those compounds, then you just assume, or it actually is, the sum of those charges are equal to 0. So I want to go through these two examples with you real quick. So I look here and I see that oxygen is -2 because it's not in peroxide and it's not oxygen by itself. Since there's 4 oxygens here, the overall charge for all of these oxygens is -8. Because I do not see an outlying charge right here, all of the sum of these charges must be equal to 0. Now, if you ever have 3 elements squished together like these 2 examples here, the way that I work it is I work the outside, the front outside, and then I look at the middle. So we already figured out oxygen overall is -8. Potassium right here is a group 1 element, and so those have a charge of +1. So now you ask yourselves, +1 plus something -8 has to equal 0. So what that is telling me is that manganese right here is a +7 oxidation state. Okay, so we have potassium, which is a +1, manganese, which is a +7, and one single oxygen is a -2 oxidation state. The reason why oxidations are so important is because when we change oxidation states, we're actually transferring electrons. We can either gain or lose electrons, and that's reduction is gaining electrons, oxidation is losing electrons. So when we look at this stuff in a reaction, we can tell if something is reduced or oxidized in the reaction and go from there. So let's look at this example real quick. And before we move along, just to make sure everyone's understanding. So oxygen here is -2 because it's not in hydrogen peroxide or it's not oxygen by itself. Since there's 4 here, it's overall -8. Since there is no outlying charge here, there's not a -2, -1, plus, anything like that. That means that the sum of all of the charges have to equal 0. Now, since there's 3 squished together, I work on this front element. Hydrogen has a rule that it's always +1 unless it's by itself or it's behind a metal. So that means that each hydrogen here is +1. Since there's 2 of them, my overall charge is +2. So now you got to say +2 plus something else -8 is equal to 0. So that oxidation state for sulfur will be +6. So one hydrogen has an oxidation state of +1, one sulfur has an oxidation state of +6, and one oxygen has an oxidation state of -2. So this is how we find oxidation states, and it's very important for us to be able to work this as we are going through electrochem. So let me move to the next slide. This slide right here is discussing the differences between galvanic and electrolytic cells. I know that a lot of you guys are getting some things confused as to what is happening in which cell. All right, so galvanic cells, the main indication that you need to know about these is that they are thermodynamically favorable. Okay, whenever it's asking for you to predict a sign for delta G, E cell, K greater than 1, you have to state this, the fact that galvanic cells are thermodynamically favorable. What that means is that the reaction that you put in the containers happens on its own. You don't have to do anything to force that reaction to happen. So, thermodynamically favorable, delta G is always negative, E cell is always positive, and K, your equilibrium constant, is always greater than 1. Electrolytic cells, on the other hand, so these are electrolytic cells, they are thermodynamically unfavorable. So anytime you have to predict the sign, justify why, you need to state that word, thermodynamically unfavorable. In this case, delta G is positive, E cell values are negative, and my K values, equilibrium constant, is less than 1. These are the main differences for galvanic cells, and these are very important things. They love to ask these questions in multiple choice and even free response. Some other differences between galvanic and electrolytic cells. Galvanic cells need a salt bridge because they are in two separate containers. All right, so you have to have that salt bridge, and remember, the whole purpose of a salt bridge is in order to balance out the charge buildup that's in your solutions. These galvanic cells are producing a battery. So you're making a battery source. Whereas electrolytic cells need a power source in order to force this reaction to happen because it's thermodynamically unfavorable. Also, just noticing the statement here, we said that galvanic cells need a salt bridge and they occur in two separate containers. Electrolytic cells do not need a salt bridge and it only occurs in one container. Now, notice here, this is the big thing. This is what doesn't change no matter which cell you're working with. Your reduction always happens at the cathode, no matter if you're working with electrolytic or galvanic. Now, if that reduction, if whatever is reducing is turning into a metal, that cathode will increase mass. So that's why we say fat red cat. Your oxidation always occurs at the anode. It doesn't matter if you're working with galvanic or electrolytic cells. Now, if you are working with a metal going into solution for your half reaction, then your anode will lose mass. Electrons still always flow anode to cathode. All right, that has not changed whether you're working with electrolytic or galvanic. Also, the way that we calculate our standard E cell values, it's reduced plus the oxidized value. Remember, we flip the sign for the oxidized value. That does not change whether we're working with galvanic or electrolytic. How we calculate delta G equals negative inphi. Okay, that does not change how we use that calculation does not change for we're working with galvanic or electrolytic. We just now know that if we're working with an electrolytic cell and we calculate delta G, it will be a positive quantity because these E cells are negative. If we're working with galvanic cells, our delta G quantities will be negative because our E cell values right here are positive. Okay, so these things do not change whether or not you're working with galvanic or electrolytic cells. Now, there's one other thing that I didn't include in this that I wanted to point out. So remember how we were talking about if you had a battery, all right, so that's supposed to be a little battery there. You have a positive terminal and you have a negative terminal on that battery. So it's just your electrodes, the metal things that are on the battery, it gives a positive sign or a negative sign. For galvanic cells, the positive terminal is your cathode. Okay? The positive terminal is your cathode. For galvanic cells, the negative is your anode. All right. I don't know if you guys can read that, but you guys get the idea. So the negative is your anode. The positive is your cathode. Okay? For electrolytic cells, it's the opposite, okay? The negative terminal is your cathode, and the positive terminal is your anode. So that is the only thing that's opposite. It's the terminals, what we would call the separate ends of the battery, that has switched between electrolytic and galvanic cells. The reason why is because since I have to hook up a power source, I'm forcing those electrons to go to the cathode. So we hook it up to the negative end of the battery. The cathode hooks up to the negative end of the power source in order to force those electrons to go through there. Okay, so this is the main differences for electrolytic and galvanic cells. You need to get those separate in your head. All right, so now let's get into the basics of galvanic cells. All right, so we're just focusing in on the galvanic cells. Here are the different parts of the galvanic cell. I think that you guys are pretty good with like knowing the different parts and everything, but let's just go through it just in case. Interesting. I don't know why that value there is there. I don't know what that's for. Okay, so here we go. We have our cathode and we have our anode. Remember, our cathode is where reduction occurs, and our anode is where oxidation occurs, okay? Now, there's a couple of ways that I can figure out who's my anode and who's my cathode, okay? One way, your cathode will always gain mass. So, if anywhere in the problem it says something about something gaining mass, the electrode gaining mass, then you know that that electrode that's gaining mass is your cathode. Your anode loses mass. So if anywhere in there it says that you have an electrode that is losing mass, then you know that that is my anode. So that's one way to determine who's my anode, who's my cathode. Here's a second way. Electrons always flow anode to cathode. So if they have a picture and they show the direction of the electrons, I can determine that which one is my anode and cathode because of how they run. They always go from anode to cathode. Notice, and I know that I've said this to a lot of you guys, your cathode isn't always on the left side. Your anode isn't always on the right side. These could be on either side. So that's why we have to pay attention into whichever is gaining mass, or we have to pay attention to the direction of electrons to flow. Okay? Now, if you do not have any of those indications, then you will have to look at E cell values. Now, this E cell value for zinc, if I were to look it up on the chart, it will be written like this. Zinc 2 plus 2 electrons yields zinc. And that value there is negative 0.76 volts. Okay? This is a reduction potential. This is a reduction potential as well. If I am comparing two reduction potentials, the more positive value, so the more positive E cell value, reduction E cell value, is always going to be reduced. Okay? So if I look at these two, 0.34, negative 0.76, this value is more positive, so therefore my copper is the species being reduced. You need to know how to be able to write your reactions. So if I'm reducing, I have to start as an ion and then go to the solid form. And there's 2 electrons that we're transferring there. Make sure your electrons are balancing out your charges. If I have to write the reaction for my anode, that is oxidized. So whenever we see these values, oxidized is that reaction flipped. So notice how the reaction that I have underneath this container is flipped from the reaction that I would see on a standard reduction potential chart. Okay? Now, because I have to flip this reaction, I also have to flip the sign. And so that's why my E cell value there is positive 0.76 volts. If I wanted to figure out what voltage that this voltmeter would be reading, all I do is I take my reduced value plus my oxidized value flipped. Then I add those two together. Okay, so reduced value, oxidized value flipped its sign, and I add those values together. That's how we get this total E cell value here. One last thing is dealing with our salt bridge, okay? You have cations, which is your positive charge things, and anions, which are your negative charge things. Your cations always travel to your cathode. So cations go to your cathode. The reason why is because this solution, because I have little copper ions jumping onto this to gain mass, to gain more mass, I'm getting rid of these little charges. So this charge overall becomes more negative. So in order to balance that out, I have to put some positives in here to balance out these negatives. So that's why your cations are always going to go to your cathode. Your anions, the negative charge things, are always going to go to your anode. The reason why is because I have more and more pluses that are coming into solution. So this solution over time is getting more positive. Since this is getting more positive, I need those negatives to balance that out. If I can't balance out my charges here, then my electrons will no longer want to flow through my wire and I won't get a voltage. Okay, so that is why it's important to have the salt bridge. It balances out these charges. If I did not have a salt bridge here, then my E cell would automatically be 0. I would not have any voltage at all. So, these are the important components that you have for your galvanic cell. Now, over time, we have some conceptual stuff here. Over time, we're going to have that reaction reach equilibrium. Whenever we reach equilibrium, we have what we call a dead battery. And we've all experienced this. We freak out when our phones are getting close to dying. And so we always have to recharge that, right? That's because the reaction inside those batteries are reaching equilibrium. Whenever we have a dead battery, these are the things to remember. Your E cell value is always going to be 0 because we have a dead battery. There's going to be no voltage being put there. If we have an E cell of 0, our delta G value is also going to be 0. And if we are working with the Nernst equation, and we're going to explain that in just a minute, where we're dealing with Q, Q now turns into K. Okay, so Q stands for reaction quotient, is for things that are not at equilibrium yet. K stands for equilibrium constant. That means I'm in equilibrium now. Okay, so dead batteries reach equilibrium, E cell 0, delta G 0, and my Q turns into K. The next principle that I want to go through is non-standard conditions. Now, when we were calculating our E cell, where we would say we would take our reduced value plus our oxidized value flipped, that was for standard conditions. Standard conditions means that I have 25 degrees Celsius, 1 atm, and most importantly, 1 molar. This is what we really pay attention to for standard conditions. If I did not have my concentrations 1 molar, then I could not figure out my E cell by the E naught equals reduced plus oxidized flipped equation. What I have to use is the Nernst equation instead. So let me give you this Nernst equation. They don't ask questions about it as often, but I still require for you guys to know it. If you ever have to use it on an exam, I will give it to you because it's no longer on your equation sheet. So, E cell is equal to E naught cell minus 0.06 over n, this is supposed to be an n, times the log of Q. Okay, so let's explain what all of this means. That is an equal sign right there. Okay, this E cell right here is your non-standard conditions E cell. This E cell is your standard conditions E cell, which is what we find from reduced plus oxidized flipped. Okay, so that is what we find from those E cell values. 0.06 is just a constant. It's some variables that are reduced. N stands for moles of electrons transferred. Okay, so moles of electrons transferred. Sorry, I got a tablet so I could write better, and it's not helping me. So I'm just going to write in gibberish cursive. So moles of electrons transferred, and where I find that is from my balanced reaction. Remember, it's the number of balanced electrons that you have. In this case, it would be 2 for my moles of electrons transferred. Q, how I find it is I plug the concentrations in of my products divided by my reactants. So notice how I'm only working with the things that have ions because those are the things that are concentrated. So let's say, for instance, that I've changed zinc to 3 molar. You see how it's no longer 1 molar. And I've kept copper at 1 molar. How I'm going to find Q is I'm going to take the products raised to its coefficient, which in this case is 1. So I would say 3 raised to the 1 over the reactants concentration raised to its coefficient, which is also 1. All right, so it's products over reactants. That is what I plug in for Q. When I'm solving for this mathematically, always work backwards when you're solving for that. So you take Q first, then you take the log of that answer, multiply by 0.06, divide by N, which is moles of electrons transferred, and then you take that whole value and subtract it from the E cell that you would find from reduced plus oxidized flipped. So that is how you work the Nernst equation. The only time you really have to do this is if it says the keyword calculate or justify with calculations. So if it's anytime talking about calculations, justify with calculations, calculate the E cell value, or if both of these concentrations were changed. So you see how this one stays at 1 molar, but this one's at 3 molar? If this one was at maybe 2 molar and that one was at 3 molar, they're both at non-standard conditions, then you would definitely have to use the Nernst equation. If that's not the case, however, you can definitely use Le Chatelier's principle in order to justify what's going to happen at non-standard conditions. So let's go back to that original value. We said that the copper was 1 molar and the zinc was 3 molar. Le Chatelier's principle, when we're working with it, anytime you have an increase in a concentration, you are always going to shift away. Ooh, I write pretty in cursive on this thing. You're always going to shift away. Anytime I decrease a concentration, I am going to shift towards. That got a little bit sloppy. All right, now when I say shift away, I shift away from wherever I'm increasing. When I say shift towards, I'm shifting towards wherever that decrease is. Now, as a result, anytime I shift to my product side, what that is causing is my E cell to increase. And so what that means is that the new non-standard E cell is going to be greater than the standard E cell, that little not symbol, that little 0 that's raised to a power or whatever, that is standing for standard conditions. So this new non-standard E cell is going to be greater than what I would calculate from my standard conditions. Anytime the reaction is shifting towards my reactants, my E cell actually decreases. And so what that means is that my standard E cell is less than, my non-standard E cell, I said that wrong, will be less than my standard E cell value, the one with the little not symbol. And again, my standard E cell value, that's how I find it. Right there, reduced plus oxidized flipped. And I will be given those E cell values. Okay, so let's go through this example problem to figure out what's going to happen to our E cell using Le Chatelier's principle. We have increased this 3 molar from 1 molar. We are increasing from standard conditions. So if I increase that, I'm going to cause a shift away, and my shift away from that increase is going towards my reactants. So since I am shifting towards my reactants, that is going to cause my E cell value to decrease. Okay, so this is how you work Le Chatelier's principle. Remember, if only one concentration is changed, not the other, from 1 molar, I can always use Le Chatelier. But if I change both concentrations, or if I need to justify with calculations, I have to use the Nernst equation for that. All right. The next thing is electrolytic cells. So, how I figure out who my anode is and who my cathode is for electrolytic cells is different from how I figured that out for galvanic cells. Now remember, for galvanic cells, we can either figure out who's oxidized or reduced by electron flow. We can figure out from something gaining mass or losing mass, or we can figure out our anode and cathode from our E cell values. Now, if we have a direction of electron flow on electrolytic cells, that's still going anode to cathode. So I can tell that this is my anode and this is my cathode. If it says something's gaining mass or something's losing mass, then that's still an indication of who's my anode and who's my cathode. That hasn't changed. But the problem with electrolytic cells is I cannot simply look at those half reactions to figure out who's oxidized and reduced. Like how for galvanic cells we said the more positive E cell value would always be reduced. That's thrown out the window for electrolytic cells. So the way that I work it, there might be other people to tell you differently. I always look to see what's in solution, okay? If I know what is in solution, then I can always figure out who's going to be reduced, who's going to be oxidized, and then that can help me determine which one of these is the anode and cathode, okay? So here's the rules. You need to absolutely know this like the back of your hand, okay? Cations in electrolytic cells are always going to be reduced. And we know that reduction occurs at the cathode. Okay? Now, this is the case if we have what you call a molten solution. Molten means that this would be just in the liquid state. Okay? But do you see how these are aqueous here? If you have something that is aqueous, that means water can play a role. So if you have aqueous conditions, it's not molten, and the cation is a group 1 or group 2, so group 1 or 2, okay? That group 1 or group 2 element is not going to be reduced. Water is going to be reduced instead. And so when water gets reduced, this is your half reaction. You have 2 H2O, so there's a 2 there, plus 2 electrons yields H2, so hydrogen's produced here, plus 2 OH minuses. This is the half reaction when water is reduced. You do not have to memorize this half reaction, but you do need to know that when water is reduced, it produces hydrogen. So let's look at this example here. What I have present is nickel 2 plus. That is my cation. So nickel is not a group 1 or group 2. So what that means is that nickel will actually reduce. And when it reduces, it'll form nickel solid. So Ni2 plus 2 electrons yields Ni. Okay, so this would be my reduction half reaction that's at my cathode. And because my electrons are traveling in this direction, this cathode right here would be nickel. Now it says that you're going to use inert electrodes. You definitely can do that. Okay, we used inert electrodes when we did our copper 2 sulfate solution, and we used the little nail or the screw for one of our electrodes. So that's totally fine. When you really use inert electrodes is if there is no solid in my half reaction. The things that we use for inert electrodes are platinum, PT, or graphite. Graphite is just carbon that's arranged in a certain pattern. We all know graphite as being our pencil lead. So platinum or graphite is what we use for inert electrodes most of the time. So we know that reduction is going to occur at the cathode and nickel is being reduced there. Now, the other rule is for your anions. Your anions are going to be oxidized. And oxidation always occurs at the anode. Okay? Now, the rule is if it's molten, that means that this is in the liquid state, then this will automatically do that. But since we have the aqueous state, that means that we have to refer to a rule. And the rule is that polyatomic ions, that's what that state, Pa ions is polyatomic ions, they do not get oxidized. Water will oxidize instead. So here's the half reaction if water oxidizes. 2H2O yields O2. Oxygen is being produced here, plus 4 H pluses plus 4 electrons. Okay, so that is my half reaction if water is oxidized. You do not have to memorize this half reaction, but you do have to know that oxygen is what's being produced here. So we refer to now our example. We already said nickel was going to reduce. Sulfate here is a polyatomic ion. So that means that is not going to oxidize. It's just going to float around in here as a spectator. So that means it's not doing anything. What is going to oxidize instead is the water that's in this aqueous solution. So I'm going to actually have little gas bubbles form at this electrode, my anode. And so what that is telling me is I have little oxygen gas bubbles being formed there. Now, if I wanted to calculate my standard E cell value, I still do the exact same thing. I still take my reduced value plus my oxidized value flipped. I just have to determine who's oxidized and who's reduced based upon these rules here. Always refer to these rules if you're working with electrolytic cells. Now here's the question. How do I know if I'm working with an electrolytic cell or a galvanic cell? Well, those main differences that I told you at the very beginning, those are the indications to know which one you're working with. Electrolytic cells will always have some sort of power source hooked up to it. So if in the problem it says that a current is applied or it's hooked up to a power supply or a battery is attached, some indication that you have a power source there, you know you're automatically working with an electrolytic cell. One of the biggest questions that we have dealing with electrolytic cells is the plating metals portion. Okay, whenever we are plating metals, we are taking a metal from an ion from the solution and we're putting it on something. The real world application is if we're plating like jewelry, if we're plating different things. A lot of these precious metals are too soft, they bend and break too easily. So we have to plate them on top of something that's more sturdy, a harder metal. And then you get your price out of how much of that precious metal is plated onto there. Okay, so when we are plating metals, we are working with the Q equals IT equation. Okay, this is on your equation sheet. However, I believe it's arranged just a little bit differently. Okay, so if you ever forget it, it is on your equation sheet. Q stands for charge, which is in coulombs. I stands for current, which you'll see written as amps, but an amp is the same thing as a coulomb per second. T stands for time. Make sure that you always convert that time to seconds. Okay? Now, they will either give you a current and a time, or they will give you some information where you can work backwards. So let's say we're dealing with copper 2 sulfate in solution. So that's aqueous. All right. Now, let's say we were plating copper onto some other piece of metal. So if I'm looking at copper, I need to first figure out what that charge or that half reaction is for the copper 2 plus. Now, I know that this is 2 plus because I basically uncrisscrossed my charges from this ionic compound. Because sulfate's a -2 charge, that means that copper must be a +2 charge in order for them to cancel out when we crisscross. So that's how I know copper's a 2 plus. So my half reaction is 2 plus 2 electrons yields Cu solid. So let me give you some information. Let's say we have 2 amps, so 2 amps, and we have 2 hours. And we want to figure out what mass of the copper is being plated. So we're looking for grams. This is how I do my approach. The very first thing that I have to do is use this current and this time to find Q. So current is in amps, that is 2. So I'm going to write Q equals 2 amps, which is coulombs per second, times time. Time needs to be in seconds. So what I have to do is convert hours to seconds. So how I'm going to do that is I'm just going to keep it in like a stitch. So 2 hours times 3,600 seconds for every hour. All right, so if I multiply all of those things, that's going to give me coulombs. And I know that because seconds is gone and hours is gone as far as my units go, and I'm left with just coulombs. Once I have converted my current and my time into coulombs, I then have to do dimensional analysis. So my dimensional analysis is I've got to go to coulombs to moles of electrons. Then I'm going to go from moles of electrons to regular moles. And then if I'm working with a gas, I can go from moles to pivnert, which will give me a volume. If I'm working with a metal though, so a solid, then I'm going to go directly from moles into grams. Okay, so I can go two different directions here. If I'm working with a gas, I can take these moles and stick it in PivNert. If I'm working with a solid, it's going to be asking me for grams. So I'm going to take that moles, convert it to grams using the molar mass. So since we're dealing with copper solid, we want to change that to grams. So I'll show you how to do that. In order to go from coulombs to moles of electrons, I have to use Faraday's constant, which is 96,500. So this number is associated with coulombs. So there's 96,500 coulombs for every 1 mole of electron. So you see now I have gotten rid of coulombs, and I'm able to cross that out there. Now I'm left in moles of electrons. They could even ask you a question and say, well, how many moles of electrons is this? Well, if I'm given current and time, I would go through my stitch and I would stop here, and that answer would be moles of electrons. They could ask for just moles. So if they want moles, I have to go one step further. In order to transfer from moles of electrons to moles, I look at my half reaction. All right, I look at my half reaction. So that's why I wrote this half reaction at the very beginning. This is my moles of electrons. This is the moles of my solid, because that's solid copper here. Okay, so there are 2 moles of electrons for every 1 mole of copper. Now you see how moles of electrons and moles of electrons is gone. And what I'm left with is just moles of copper. Now, if I wanted to go to a volume, if this was a gas, then I would take this moles and plug it in right there for N in PivNert. They would have to give me a pressure, and they would have to give me a temperature in that case if I was solving for volume. But since this is a solid, I'm going to go directly into grams. So I'm going to do one more stitch here. To do one more stitch, I'm going to transfer moles to grams by using the molar mass. So 1 mole of copper is equal to 63.55 grams of copper. So now what I've done is I've gotten rid of moles of copper and I'm left with just grams. So now all I have to do to find my answer is multiply across, multiply down here, and then divide the 2 quantities. And that will give me grams of the copper that I would want. You will have to be able to do this on multiple choice as well as free response. Okay? If you're working this on multiple choice, then you do not have to do the mental math. You would have to set this all up into one big long division equation. And I think we've had some examples with that. Also notice that they could give you grams and you can work backwards. So if they give you this gram amount that you're starting with, you would have to just work backwards. You would have to find moles, and you would have to find moles of electrons, then you would find coulombs, and then you would stick it into this equation here. So this is if you were trying to find current or if you were trying to find time. They would give you one of these 2 values. They would give me something like this. And so I would solve for coulombs, plug that in, plug in the other information that they give me to solve for the unknown. So this is a huge part of electrolytic cells, so make sure you know how to do it properly. Now, for our very last slide, we're going to talk about the delta G equations, okay? There are 2 delta G equations that you need to know for this unit. The first one is delta G. This actually should be delta G. I couldn't find the delta sign because there wasn't an insert equation thing. Oh well. Delta G is equal to negative Nphi. Okay, don't forget that this is a negative sign right there. Okay, remember, if it is thermodynamically favorable, that's for galvanic cells, you should be getting a delta G that is negative there. If it is thermodynamically unfavorable, that is for electrolytic cells, then you should be getting a delta G that is a positive quantity. So always go back and double check, because a lot of people forget that negative sign there, but it needs to be there. Okay. The reason why it's thermodynamically favorable, delta G is negative, is because remember, galvanic cells get positive E cell values. Electrolytic cells, the reason why you get a positive delta G quantity is, remember, electrolytic cells get negative E cell values. Okay. So this N stands for moles of electrons transferred. Okay, so where I find this is my balanced electrons from my half reactions. F stands for Faraday's constant, so that is 96,500. And E is your E cell value that you found. Now, if this has a little not symbol, so standard conditions, then you're going to find your E cell from your reduced plus oxidized flipped. But if there is not a little not symbol there, and you will know because they're not 1 molar concentrations, you will have to find this E cell from the Nernst equation, and then you would figure out your delta G. Okay, so I can do this equation for both galvanic and electrolytic cells. It's just the sign that I get for delta G will be different. This equation right here, the only time you really use it, now I'm sure there's other times, but the most time that sticks out in my head is if you're trying to solve for K. Okay, I call this the delta G equals negative Ratlink equation. Okay, I would have found delta G previously using this equation here. Now remember, when I solve for delta G here, because N stands for moles of electrons, so that's the units for N. F is coulombs over moles of electrons. And E is volts, which a volt is a joule per coulomb. If I look and cancel out everything, moles of electrons is gone, coulombs is gone, and I'm left with joules. So when I calculate delta G here, that unit is joules. Now, AP got a little fancy, and they said, well, it's not just joules, it's joules per mole of reaction. So they want you to specifically put joules per mole of reaction. What this bottom portion is saying is that one reaction go along from reactants to products is going to give me that amount of energy. If I were to go a second time through that reaction, I would get twice that amount of energy, and so on and therefore. Okay, so it's joules per mole reaction. Be careful, because sometimes when you calculate delta G, because most of them are really large numbers, they are going to want you to have that answer in kilojoules per mole reaction. So make sure you are aware of which one it's indicating. If it doesn't specify, it's okay to leave it like this, but you have to put the units down or else you wouldn't get credit. In order to convert from joules to kilojoules, what I would do is divide this quantity by 1,000. In order to convert to kilojoules to joules, I would take this quantity multiplied by 1,000. So remember, 1,000 is our conversion factor between these two. Now, back to what I was saying about delta G equals negative Ratlink. You have to be careful, because this R value that you use is 8.314. It is not the same R value that you would use in PivNert. The reason why is because you need to make the units cancel out. So the units for this R value is joules per mole Kelvin. So when you plug in delta G here, you have to make sure that it's in that form, joules per mole reaction. The reason why is because we have to make these two units right here cancel out. So you have to use this value. You have to make sure delta G is in joules. T stands for temperature. That must obviously be in Kelvin. Remember, this is a little negative sign there. There's a little negative sign in negative Nph. Don't forget that. These two equations are on your equation sheet. Natural log is ln. Most of the time you're trying to find your K value, so you'll have to take the inverse natural log, which is e raised to the answer. And I'll show you that in just a second. And then K is your equilibrium constant. That's mostly what you're trying to find. So if you need to solve for K, this is how you work it out. You take your delta G. Remember, it must be in joule form. You divide by negative RT. And that value is equal to natural log of K. All right. What I'm going to do now is get K by itself. And how I do that, this right here is going to be some quantity, some number, when I do that in my calculator. So to get rid of natural log, I'm going to say E raised to that number, I fishhook it, E raised to that number is equal to K. So I can definitely leave the answer like this, or if I put this in my calculator, there will always be exponents, some number times 10 to the something, whether it's negative something or positive something. Don't forget this part, okay? You got to look at the whole part in my calculator. Make sure you put your proper 10 raised to whatever power scientific notation as your answer, or else, boom, they will count it wrong, okay? So this is how I work my delta G equations. Now notice, I can work these for either galvanic or electrolytic cells. All right, guys, I think that's all for the crash course. Let me know if you have any further questions. We will have our test on Thursday, and single period, if you're watching this, your test is on Friday, and I hope this helps a little bit. So that's enough of that, and good luck on Electrochem.